Hello again, everyone. Last time we started to add some really nice behavior to our network class right here. We started to add a behavior that takes care of adding a node or removing a node or removing an edge. We're still missing an important function here, which is a function that's supposed to be adding an edge. That is what we need to add next. So remove an edge is add an edge is very similar to remove an edge. It's going to take the same number of parameters that we worked with when we removed an edge. Okay, so now what we need to do for adding an edge, well, first of all, we have to ask, an edge is nothing but two components that are connected together by a relationship. In terms of a dictionary, C has a relationship with an A, which means C is connected to A if A appears in the values of the list of the key of the dictionary. This is exactly what it means to have a relationship, to have an edge between two nodes. So what we really need to do here before we start connecting things, we have to see if they are connected or not. But more important than anything else, we also have to see if these guys, if the left and the right, are in the keys or not. Suppose now, and let me show you. If I work with this graph here, I know that F is in the network. I know that C is in the network. But I also know that F and C are not connected, correct? So now if I'm going to add an edge, between F and C, I don't need to add the nodes because the nodes are already there. So what I need to do is to check if these nodes are already there. If they are there and I need to connect them, then I basically end up listing. So if I have F and C, then maybe what I need to do, I need to make sure that C is also listed here as well. So that means C is also having an edge. F has an edge between with a C, but C is already here, so we don't need to add it here anymore. What we need to do is to simply append it to the list of values that belong to the key F. This is exactly what we're going to implement here together. So let's get started. Well, first of all, what do we need to do? We need to ask if left is in the graph or not. How do we do this? Well, it's going to be simple because we can say if left is in the keys of the graph, and the graph here, we as you can see, we can utilize this part here. So the graph has the graph object, or the network object has the graph dictionary, and the graph dictionary can be accessed. The keys of this graph dictionary can be accessed using the keys function. So by doing here this, now I know for sure if left is in the graph or not. If it's in the graph, then I don't need to add it to the dictionary. I don't need to create another key because it's already there, right? So what I need to do if left is in the key, now all I need to do is to basically add right to the values of that key here. So this is, in this case here, what I need to do is to get the dictionary, and I'm going to reference the key, which is the left node, and this is going to give me the values. It's going to give me the value of that specific key here. And what I need at that point is to append. I don't have to do it in one stop. I can basically access, because this is going to give me a list, which is the value, and the value is a list. So now what we need to do is to invoke the append, and then we add the right node to the set of keys that belong to this, the set of values that belong to this specific key here. Okay, this is good. Now, what if otherwise? What if this guy is not? Else, what do we need to do? Well, if it's not there, then we need to create it. Suppose I want to add, we have A, B, C, D, E, F. Suppose I want to add G, and G I want to connect it with another one, right? So what I need to do is to basically add one of those guys. So else, what I need to do now, which means if left does not exist in a graph, then I basically have to create an item for it in the dictionary. And this is really simple here. So now if left does not exist, like say in this case the node G is not available, then what I'm going to do is to assign right to it as a list, like that. So here I'm being consistent, that I'm making sure, because if it's not there, then it doesn't have values, and the values that we're creating are coming from lists. Remember when we added a node here, I would like to remind you, this node came with neighbors, and these neighbors were actually a list of individuals that were connected to the node here. So I want to be sure that we understand now that even though that this node now doesn't exist and I'm going to add it, but the value is going to be a list, even though it has a single item in it. Why? Because I can eventually add G here, right? So it's not foreign that there is a single item, a single key that has a single value list. In this case, it's not foreign because we also have E is connected to a set of values, and this set of values only has one single value, which is B, and F is the same story. So we just want to make sure that we add this here as a list. Okay, but remember, if I do this, if I connect F to C, okay, if I do that, this is great, I'm done. But if I am going to check if C is connected to F, they will not be connected. Remember, this is an undirected graph, so I have to make sure that as much as I connect F to C, I also want to make sure that C is also connected. So here, if I want to connect F to C, like that, I also want to make sure that C is connected to F, so I want to add F here. That's what I'm gonna do. That's how I'm going to show you now. So doing so, we have to do it from left to right, but we also have to connect it from right to left as well. So let me do the same thing here. We are going to ask if right is in the keys, right? In self dot underscore underscore graph, and then I'm going to invoke the keys function. So now I'm asking if right is in the keys, then that's great. I don't need to add anything. I don't need to create another key for this graph. All I need to do is to append the left to the value, because I already know that I already have a key, and this key has a value, and this value is a list. So what I need to do now, I basically need to add the left. So now because I'm asking about the right, and the right is my key, now I'm going to append the left. So I'm basically doing the exact opposite of what we've done here. So if right is in the list, then great. All I need to do, in this case here, if I want to add G, and I know that the edge that I want is F and G, I know F is already suppose that I want to do G and F, or F and G. F is already in the network, that's great. Now all I need to do is just append G here, like that. Okay, so this is exactly what we're doing here. If left is in the graph, sorry, if right isn't a graph, then we basically append the left. Otherwise, we create a new key, and this new key here is going to be, again, we're doing this from the perspective of the right versus left, right to left. So now I'm going to make the right node to be my edge. I apologize, the right node to be my key, and the key is going to be connected to the value by creating a list, and this list will only have a single value, which is a left. So now we connected left to right, and we also connected right to left. If we do this, we should be okay, I think. And what I really like to do here is to always return the graph after I modify. I think it makes a lot of sense. So you can see when the function here, when you add an edge, you get back the graph, and you see that the graph is indeed showing that it has a new edge here. So I really want to try this. I really want to make sure that I try in a few with a few test cases. So how do we do this? How do we test this functionality here? Well, there's nothing for it. Let's run the class here. We ran the class code, and let's work with this data here, okay? And let's create a network object like that. And I don't want to remove anything. As a matter of fact, what I want is to add an edge at this point. I want to add an edge. So what edge do I need to add? Maybe I want to add C and F. Why not? So C and F, because we don't have C is not connected to F, and F is not connected to C. So C and F, it's the same example that we used when we're implementing this. So we really want to make sure now that if we are adding, let's just do it like C and F. So what we need to do, if we run this, we need to see a dictionary, right? That has C connected to F in the list here, and also F being listed here in the list of in the values of C, which is essentially a list. So we need to add C to this list here, and we need to add F to this list here. But we also know that F and C are already there. So this is one good case scenario that we're gonna try. Let's do this and see if we're gonna have any errors. Okay, we have some errors here. All right. Maybe I mistyped something. Well, it's called keys, not key, for sure. I mistyped it. So let me run this one more time. And we already have these guys in memory. So let me run a new object again with the new definition of the graph. And then I'm going to run this one more time. Okay, now I want to see the new dictionary. So let me print this new dictionary. And okay, it seems that we've done something. I see what happened. So the first half of the function worked. What we need to do, let me do this. Let me show you. Because the list does not ensure unique values. It's a set that ensures that. But half of the function worked, and the second half didn't work. That's why you see the C twice, you see the F twice, and you see the C single time. Because half of the function was executed because that was correct, and the second half was not executed because the word key does not exist. So let me run this one more time. We're going to run the graph definition again, and let me initialize the graph again and create a new object. Okay, and then let's create a network object here. And now if I show you this is going to be a single F here. As you can see, we have a single F. Actually, I don't know if it will look much better if we count on. Here we go. So as you can see now, um, now we have a link from F to C. Not a network yet. We have not visualized the network yet. Remember, we only run it up to that point. But I want to show you on the graph, even though it doesn't look connected yet, but I want to show you how it will look connected after we do the visualization. But for the time being, let's take a look at the dictionary. The dictionary here has an item in the values, which is C. So basically F is pointing to C. But also from C point of view, we have to have C here exist, and C is also having a reference to F. That means that F is connected to C, and C is connected to F. So it's bidirectional. This is exactly what it means to be undirected, which means this is F is connected to C and C is connected to F. Let's construct the graph object using network X. I believe we don't have network X in the memory anymore, so let me import network X as an X like that. And now when we use the reference for network X, it will recognize it. But if I did this earlier, it would not recognize it. I believe we removed it last time when we did the lesson, because it was we've done it once and it was already in memory, but then we're starting fresh again, so it was not in memory anymore. So I'm gonna run it here, and then let me show you if we run this object, if we run the draw function on our object here, on our graph object, using the dictionary here that we populated with the add function, we should have a link from F to C and then C to F. Clearly, we're only going to see one line, but this line in the dictionary actually will mean that there is a link from C to F and F and C to F and F to C. Let me run it. So all the curiosities are killed. Here you go. Where is F? So F and C, and as you can see, the graph is rendered every time differently because we are using the default layout. If we want to see the same graph every time, we can specify the random layout, and then we can specify a seed. But for the time being, as you can see, this is really great because now we can see that F is connected to C, and also C is connected to F. Again, you only see one arrow, but in the implementation here, you know for sure that F is connected to C and C is connected to F. This is exactly what it means. What might be useful at that point is to actually implement a function that asks if the graph contains an edge or not. I'm just going to as edge like that, and it's gonna take this like that. We have an extra thing here. So in this situation here, I'm basically asking if a left to right exists or not. At this point, I'm not asking if it's bidirectional. I'm asking if there is an edge from left to right. Okay, this is exactly what I'm gonna ask. So now I wanna be sure if left is already there, if left is in the function, in the dictionary keys, then I know for sure that it has a value, and then I can check the value. If right isn't the value, then I would say yes, this edge exists. If one of those guys don't exist, say the left does not exist in the dictionary, then I know for sure that the edge does not exist. There won't be an edge without two different components in it. So let's get started. So we can say if the left in the graph, so that would be self underscore graph like that, and I'm gonna get the keys. Okay, so now if the left is in the graph. Okay, so now I'm going to ask if right is in the graph or not. How do I ask that? Well, I'm gonna get the list of values using the key, and the key here is my left. Okay, so this is going to tell me, is going to give me the list of the values. Now I can immediately ask and I say, well, if right in the set of values, then I can say return true. That is the only way I'm gonna return true. Oops. Otherwise, I am going to return false. So the only way I'm gonna return true if I know that these two guys exist. Otherwise, the function, so if I get here, if I get into this statement here and I return, then the function is not gonna execute this line. But if I don't get here, then the function for sure is gonna tell me, I'm sorry, mate, I don't have that edge that you're looking for. So now let's try to test this function here. Where is our graph? Our graph is called collab G, okay? And let me create a few cells here. So now I'm going to ask, but before I do that, I'm going to run this guy one more time. So I make sure that it's in the memory, and I'm going to run this guy too. Oops. So we basically reverted into the previous version of this. So this graph now is not going to know anything about C and F. Okay. But now I'm going to ask if C is connected to F. But I'm not going to add them. I'm just going to ask at this point if C is connected to F. And this is going to give me the result. Okay? And I am expected to have a false value here. I'm going to print result like that. And assuming that I've done everything right, I am not going to have any errors, but let's see. Okay, it says it's not there because we know we started with this graph again, okay, for sure. So this graph did not have, and let me show you. I'm going to visualize this graph to show you that F and C are not connected. Here, F and C are not connected because we used the older version of the graph before we connected them. Okay, let me also ask from the other way around. If F is connected to C, because remember this is an undirected graph. So now F, it becomes my source and C becomes my destination. Unlike this one, S is a source and F is a destination. So in this case, I'm supposed to be getting two false. False and false. Very good. Okay. And if I visualize again, F is not connected to C. As you can see, C here and F here, so they are far away from each other. All right, let's do something interesting. Let's connect F to C. Let's do that. How do we connect F to C? Well, we need to add an edge. We just implemented that. So my graph name is collab G. This is our network object. Collab G dot add edge. So I want to add F to C, right? And this is supposed to give me my new graph, which is a new dictionary. So let's do this. Now I want to print So when we added an edge, we made sure that we added F to C and C to F. Because again, the graph is undirected. If we say that this graph is directed and direction matters, then I'm only allowed to do it from F to C this way. And I'm not supposed to see that one. That's the reason why we implemented it this way, because we wanted to make sure both of these two things are actually connected together. Okay, so now let me get back here. Let me construct a new graph, a new network object, network X graph, right? And I'm going to pass the new graph after we connected the edge, right? And let me run this one more time. Now, F and C are connected. Very good. All right, so now if we go back here and we run these two guys, what are we going to say? What are we going to see? Let me make a little cell here, like that. So now we can ask, I'm going to ask if C is connected to F. C is connected to F. And here I'm going to ask if F is connected to C. F is connected to C, like that. But let me run them one at a time. This is supposed to give me true now. Very good. And now this is also supposed to be giving me true. Remember, because before I show you the code, let me make sure that I run this here too. I'm gonna run it here. And it's saying that F is indeed connected to C. So F is connected to C and C is connected to F. If we have forgotten to have the left turn from right to left and left to right, if we did one of those, if we do left to right, then one of them is going to be true and one of them is going to be false. So if we did from C to F and we did not do from F to C, then we would probably see that this is right. Well, not probably, I mean for sure. And we're going to see that F is not connected to C is false. So as you can see in an undirected graph, we really have to be careful connecting things from both directions. This is good. So to recap for this video, we added an edge from both directions, from left to right and right to left, because it's an undirected network. And then we also checked if the edge exists or not. We asked if the network has an edge or not. But in this case, we basically asked if the edge is from left to right versus right to left. Because if I am asking if my edge is constructed from left to right, and it's only an edge. And if I want to swap the order, I can say from right to left. So like we did here. Then if we did it right, then it's gonna be available. Then this guy is gonna be there. But we have to ask with the right order. If we in a directed network, these two guys are not going to hold true. One of them is going to hold true and one of them is going to hold false, like in a two-way street. In a two-way network, I apologize, in a one-way network, you will find the direction from C to F, but not necessarily from F to C. You will not find that. So this is exactly why we had to check that both directions existed and both of them are true in this case here, because we treated, here's a true here and here's a true here, because we treated the network implementation as an undirected graph, and we made sure that when we connect, when we add an edge, we add it from both ends. We add it from left to right and from right to left. This is good, and I know this is probably a lot, even though the code is not very much, but the concepts behind this is a lot of things to think about. So I should probably let you meditate with this code and play with it for a little bit. And if you have any questions, if you have any comment, please write to me and let me know. And as always, thanks for watching.